All right, so now let's move to question 1.4, which says, which of the following state visualization represent the same quantum state as shown in this Qsphere? And we're given a Qsphere for a particular state, and we'll go over what this means. And we're given a few options, and what we need to try to figure out is these options, which of them represent the same state as is depicted in this Qsphere. So we're given a state-city plot, which we covered in the previous video. We're also given what is known as a Hinton plot, and we'll describe what this is. Also, this representation, which is known as a Pauli Vector representation, we'll also explain what this means. And lastly, a state represented using bloch spheres. So before trying to understand which of these plots represents the same state, let's go over the Qsphere to try to figure out what state is it representing. So let's go here and do question 1.4, and let's draw here a sphere, and this sphere has two, let's call it sticks, two sticks, one going up and another one going down, and they were labeled with state 0, 0 and state 1, 1. So the first thing to notice here is that this little sticks have a blob at the end of them. And what that blob represents in the Qsphere is the probability amplitude, or the magnitude of the probability amplitude associated with each state. So what that means is that the larger this blob is, the more probability amplitude is associated with the state 0, 0, and similar for state 1, 1. Now here they're about the same size, so that means that the magnitude of the probability amplitude for these two states has to be the same. So first off, let's remember that in general we can represent a state, let's call it psi, as a sum of some probability amplitude, let's call it alpha n minus 1, times a basis state a n minus 1 plus alpha 1 a1 plus alpha 0 a0. So this is just a general representation of a quantum state, where each of these alphas, so let's say alpha sub I, it's a complex number, right? And for I from 0 to n minus 1, right? So what this means is that this alpha sub I can be expressed as a sum of a real component plus an imaginary component, right? But another way to express alpha is by using the absolute value of alpha. Let's change the color here. Let's say the absolute value of alpha times e to the I, let's call it phi I, where this is the magnitude of this component, and phi it's its corresponding phase. So we can represent alpha in either of these two ways. So that means that in our specific case, for this specific example, where we have a state associated with or a state in superposition of 0, 0 and 1, 1, we can express, let's call it also psi. We can express that state as some probability amplitude, let's call it alpha 0, 0 times e to the I phi 0, 0 times state 0, 0. plus, say alpha 1 1 e to the I phi 1 1, right? So this is the state associated with what we're plotting here in this Qsphere. And what we know now is that since we said that the blobs of these two states in the Qsphere represent the magnitude of their probability amplitudes and they're of the same size, that means that alpha, say alpha 0 0, has to be equal to magnitude of alpha 1 1, and since the state has to be normalized, these two have to be equal to 1 over root 2. Okay, so that's the first thing to note. The Qsphere is telling us that we have a state in equal superposition of 0 0 and 1 1. Now, the next thing to note is that the color of this sticks represents a phase, and I don't know if you remember this from the problem statement, but this Qsphere had a little wheel here on the side which had some colors associated with it, and I'm gonna only show a few colors here. It's like a continuous changing color, and the colors represented a phase, and here on the right we had a phase of 0. Here on the top we had a phase of pi over 2. Here on the left, phase of pi, and here at the bottom a phase of 3 pi over 2. So this means that associated with the state 0 0 we have with the state 1 1 we have a phase of 0, and associated with the state 0 0 we have a phase of pi. All that means is that this phi 0 0 is pi, and this phi 1 1 is 0. So now let's rewrite that state again, now that we know all its components. So we know alpha 0 0 is 1 over root 2, and then e to the I pi times state 0 0 plus, and again alpha 1 1 is 1 over root 2 e to the I 0. So we know that this is equal to 1. So we can rewrite this state as phi equal to 1 over root 2, and then ei pi 0 0 plus 1 1. Now, when working with quantum states, it is usually the convention to leave the 0 0 state with no phase associated to it. So we can actually pull out this e to the I pi so that the state 0 0 doesn't have any phase with it. So I'm just going to move here to the left and rewrite that again. So we have 1 over root 2 e to the I pi, and then we have again our state 0 0 plus, and now since we had no phase associated with the state 1 1, well, we need to add a phase of minus pi here, so that if we distribute this back in, well, we know that ei pi times e to the I minus I pi is equal to e to the I pi minus pi, which is e to the I to the 0, right? So equal to 1. So then to factor out this e to the I pi, we have to add this extra phase on the state 0 0. So, but what is e to the minus I pi? Well, that is just equal to minus 1. So the state psi is equal to 1 over root 2 e to the I pi of state 0 0 minus state 1, 1. Now, the other thing to keep in mind is that this is what is known as a global phase. And what that means is that it has no repercussion on our probability amplitudes, because when we measure states and we get probability amplitudes, we always take the norm squared of them. And whenever you take the norm of e to the I to some phase, that's always going to be equal to 1. So this state is exactly the same as just having 1 over root 2 times 0, 0 minus 1, 1. So this is now the state that is represented in the bloch sphere up here. And the next step is for us to figure out what is the different ways we can visualize this state, so we can figure out what's the correct answer to the problem. So let's go ahead and start with the statecity plot, which, if you recall, we went over this in the last video, but now we're going to do it for a different state. So again, the statecity plot is a visual representation of the density matrix associated with our state. So as before, the density matrix is given by the order product of our state with itself. So multiplying the ket of our state times the bra of our state. So if we now represent the state in as a column vector, we know that the state is given by 1, 0, 0, minus 1. So this is the same as the state we have above. So this is the ket component of it. And now we're going to do matrix multiplication with the bra version of this. So the bra version is, again, we have 1 over root 2, but now we have a column vector of 1, 0, 0, minus 1. Okay, so we can now do 1 over root 2 times 1 over root 2. That gives us 1/2. And then since we have a 1 by n matrix here and an n by 1 matrix here, right? We know that the result is going to be an n by n matrix. Or in this case, well, 1 by 4 and a 4 by 1, right? So we know it's going to be a 4 by 4 matrix. And the easiest way to do this is to just take the row vector and multiply it by each of the components of the column vector and just go down the line. So if we do here in this case 1 times our row vector, well, we just get that same row vector, so 1, 0, 0, 1. Then if we multiply 0 by that same row vector, well, we're just going to get zeros, 0, 0, 0, 0. Same for the next one, 0, 0, 0, 0. And sorry, I made a mistake here with the sign. This is minus 1. Let's move this a little bit up here. And then lastly, we multiply minus 1 by, again, the whole column vector. So we get minus 1, 0, 0, 1. So this is our density matrix representation of our state. And if we were going to represent this in a statecity plot, well, we can simply place these bars in our grid. So we have here state 0, 0, state 0, 1, state 1, 0, state 1, 1, and similarly state 0, 0, 0, 1, 1, 0, and 1, 1. So we know that we have in our matrix, we have here 0, 0, and using Qiskit's order for bits or qubits, we have here 1, 0, 0, 1, 1, 1, and similarly 0, 0, 1, 0, 0, 1, 1, 1. So associated with the position 0, 0, 0, 0, we have a 1/2. So in our plot, we'll have a little column here, or a building, right? In position 0, 0, 0, 0. Then in position 1, 1, 1, 1, we'll have again little column here, both of height 1/2. And then for position 0, 0, 1, 1, we have a -1 here. So what we're going to get for this particular state is actually a bar going downwards. And you can imagine this plane is, we're seeing through the plane here. And then similarly for position 1, 1, 0, 0, we have another column going downwards here. Right, and this is, this will be our city plot. Now all other locations, they just have probability amplitude of 0. Okay, so before moving forward, let's go ahead and implement this in Qiskit and see if we can match that state representation. So let's go ahead here and start by importing from Qiskit quantum info, import a state vector class and a density matrix class, and let's also import numpy as MP. We might need this to initialize our state, so let's run that. Let's go ahead and say our state psi is 1 over root 2 times state vector, and we're gonna let's define it using the list of elements of our column vector, which is 1, 0, 0, -1. And then let's take a look at our state, and this is in fact 1 over 2, 0, 0 minus 1 over 2, 1, 1. And as I showed in the previous video, one thing we can do here is, instead of importing all these visualization functions, we can just do psi.draw, and then here we can do Qsphere and let that draw, and here we can see that this matches exactly the image from the problem statement. So we're in good shape. We did derive the right state here. So next, well, actually, before moving to the next visualization method, let's not forget to draw our statecity plot. So here we'll do psi.draw, and we did this in the previous video as well. We do here's city, and here we can see that, as expected, as we derived, we have on the 0, 0, 0, 0 location a positive bar of about 0.5, which is what we expected, similar for the 1, 1, 1, 1 location, and then on the off-diagonal terms on the 1, 1, 0, 0, and in the 0, 0, 1, 1 location, negative bars of -1/2, as we had shown in the derivation. Let's move to what is known as a Hinton plot. So a Hinton plot is actually very similar to this state-city representation. It's a visual way of expressing our density matrix. Now, instead of having this kind of 3D landscape of buildings sticking up and down, what we have with the Hinton plot is basically a grid. So we have a grid with locations 0, 0, 0, 1, 1, 0, 1, 1. Same 0, 0, 0, 1, 1, 0, 1, 1. And each of these locations gets associated with it a little box. And the size or the area of that box represents the amplitude or the magnitude of the parameter or the item in that location of the matrix. So in our matrix, we know that location 0, 0, 0, 0 has an amplitude of 1/2. So you will get a little square here of some area that represents that 1/2. Similar for location 1, 1, 1, 1, we have another square of actually the same area as the one above. And then to specify negative values, the color of that box just changes. So in the case of location 0, 0, 1, 1, you have a darker box. But since the amplitude associated with this, or the probability associated with that location, is -1/2, and with these other two locations is 1/2, same magnitude, then the area of the square is the same, and it's same for the one at the bottom. Now, if the values of each of these locations weren't the same, what you would find is that the size of the boxes will be different. So locations with larger values in the matrix would have larger boxes associated with them, and smaller boxes. So that's it. So now let's go back to Qiskit, and we can draw the Hinton plot associated with our state in a similar way. We do side.draw, and here we just specify Hinton. And here we go. Here we have it. So here we see that positive values are associated with a white box, and negative values with a black box, and all the other locations have also boxes associated with them, but because the amplitude of that location is 0, then you just get a gray box on each one of them. Again, similar for the imaginary component, it's all gray because every value in there is 0. So the Hinton plot and the state-city plot are very similar to each other. Now, next, we have what is known as the Pauli Vector plot. Now, before going into that, we can see that actually this Hinton plot matches option 2. So this is the correct answer for this problem, is option 2. But just for fun, let's go ahead and try to understand what this Pauli Vector representation is, and what is it that we're looking at here. So now let's go here and do Pauli Vector representation. So for Pauli Vector, what we have is that the composition of our density matrix in what are known as the Pauli matrices. So for this one, let's start with a very simple example again. So let's do one example with a single qubit. So single qubit, and let's specify the state psi equal to 1 over root 2, 0 minus 1. Okay, and we've derived this before. The density matrix associated with this state is equal to 1 over 2, 1, 1, minus 1, minus 1. So for density matrices, one thing to know is that similar to how states can be decomposed into basis states, matrices can be decomposed into basis matrices, and the basis set for these matrices is the identity plus the Pauli matrices x, y, and z. So just a reminder, you know, the identity matrix is just 1, 0, 0, 1. X matrix is 1, 1, 0, 0 here. The Y matrix is 0 minus I, 0. And the set matrix or Z matrix is 1, 0, 0, minus 1. So it turns out that a single qubit density matrix can be expressed in the form 1/2 times some magnitude, let's call it A sub I, times the identity matrix, plus another amplitude A sub X times the Pauli X matrix, plus AY times the Y matrix, plus AZ times the Z matrix. So in general, any density matrix can be decomposed in this way, and this can be also generalized for n qubits. So in the case of so for 2 qubits, now your bases, your matrices that form your bases are actually the Kronecker product, or the tensor product of the Pauli matrices plus the identity. So that the basis would be matrix I, so this is I cross I, IX, IY, IZ, XI, and so on until you get to ZZ. So what we'll find out is that there's a total of 16 matrices. So for 1 qubit we had 4. For 2 qubits we have 16 matrices. And similarly, we can decompose a 2 qubit density matrix as something similar to what we have here for 1 qubit. Now in general, any density matrix can be expressed as 1 over 2 to the n, where n is number of qubits. And then we have the sum of I from 1 to j, where j is the total number of matrices times some coefficient ai times p sub I, where p sub I is what's called a Pauli string. And a Pauli string is just basically the multiplication of this Pauli matrices and the identity. So in the case of 2 qubit states, our Pauli strings are this II, IX, IY, and so on. And then let's just write this down. Oh, I already wrote it down here. J is the total number of matrices, which in general is actually 4 to the n, where again n is the number of qubits we have. Okay, so let's go back to our specific example where we had, or this specific problem we're dealing with, where we had the density matrix 1/2, 1, 0, 0, 1, 0, 0, minus 1, 0, 0, 0, 0, 0, 0, 0, 0, minus 1. Right? That's the problem we've been dealing with. So here what we have is we can decompose this matrix into 1/4 and the sum of I from 1 to 16, as we said before, times AI pi, and again this pi is II, Ix, so on until CZ, right? Now the question here is, how do we calculate these coefficients? And the way to do this is by computing the inner product of our state with each of these polystrings. So for example, the coefficient AII will be calculated by doing the inner product between rho and II. And the inner product for matrices that is used here is called the Frobenius inner product. It's given by the trace of our matrix II. Well, we have to take actually the Hermitian adjoint of that times matrix this is matrix multiplication times rho. And just as a reminder, the trace is just the sum of all diagonal terms of whatever matrix you have in here. And you can keep calculating all this coefficients just by computing inner products between our state and all the different polystrings. For our example, I won't calculate what these values are, but what's important to know is that this Pauli Vector plot, what it's going to give us is basically the amplitudes associated with each of the components of the different polystrings for our state. So if you have some probability of or some coefficient AII of, let's say, 1/4, then you will get a little bar here on II, then let's say minus 1/4 for Ix, you will get that here, and so on and so forth. So instead of calculating it for our state, which might take quite some time, let's just go here in Qiskit and just draw it for our state vector. So again, similar to what we did with the city plot and the Hinton plot, we just go here and do psi.draw and replace here Hinton with Pauli, I believe it's Pauli Vec. That's right. And then here we have it. So our state has a decomposition of II, XX, YY, and ZZ, and each of magnitude 1/4, where XX is minus 1/4. We can go back and verify that, in fact, when we add up these matrices, we will get the density matrix of our state. Okay, and last up we have the bloch sphere representation. Now, it is easy to tell that this is not the right answer, because what we have, our state vector, it's a maximally entangled state vector, and this bloch spheres that we're seeing here have vectors that represent individual qubits, so qubits that are not entangled. So in this particular case, if we have now a bloch sphere for, let's say, qubit 0, qubit 0 with the vector pointing along the x-axis, like in this case, we know that that means that qubit 0 is equal to 1 over root 2, 0 plus 1. And if we have a separate bloch sphere, like in this case, for qubit 1, let's put it over here for qubit 1, where now we have a vector pointing downwards. Well, we know that the north pole we have state 0, south pole we have state 1, here we have state plus, state minus. So we know that qubit 1 is in state 1. So our total state psi for this bloch sphere representation, it's given by Q1, Q0, or separating them, Q1 tensor Q0, which is equal to state 1 tensored 1 root 2, 0 plus 1, which is equal to 1 over root 2, 1, 0, plus 1, 1, which is not the state that we had derived, which was state 0, 0 minus state 1, 1. And again, we can go to Qiskit and see that because our state is a maximally entangled state, we can do psi, draw, and we can do bloch here. We see that there are no vectors for this particular state, which means this option is not correct either. So as we said before, the solution to this problem is option 2.